Let's have a look at the parts of the wheel and how they all fit together. As a complete unit, we call this the wheel. On the outside, the rubber part that gives us traction is the tire. Inside the tire might be an inner tube, which acts as a bladder to hold the air pressure. Or you might have a tubeless system that maintains air pressure without an inner tube. Next, we come to the rim, which is basically a hoop. Inside the rim is commonly a rim strip, which protects the inner tube from holes and the spokes in the rim. Tubeless tire systems commonly use special tapes to seal the inside airtight. Now we come to the spokes, which are basically long, skinny fasteners. Spokes typically attach to the rim using nipples, which are the nuts of this fastener system. The other end of the spoke attaches to the hub at the center of the wheel. The hub contains a bearing system that allows the wheel to rotate. The wheel is then attached to the frame or fork, and off we go. Let's start over for a more detailed look at these component parts. While we normally don't consider the tire while chewing the wheel, the tire is where the rubber meets the road, and so it is important for the wheel's performance. If the wheel is improperly seated or is damage to the casing, it can look as if the wheel has spoke truing problems. This is one reason why it's useful to have the tire removed when you are just learning to true wheels. Rims that are made of steel or aluminum begin as a straight channel that is cut to length and rolled into a hoop. The hoop is then joined by pins at the seam or is welded. Carbon fiber rims are made in a mold. The rim and hub each have matching number of holes for spokes. This hub has 16 holes on each side, and this rim has 32 spoke holes. Rims are somewhat flexible and actually flatten slightly on the bottom as you ride. That means the spokes at the bottom will slightly slacken as they pass to this lowest point and then gain tension again. However, the biggest concern for the rim is not this normal stress of flexing, but the damage a rim might take from impacting things or crashing. Bicycle spokes can be made of steel, titanium, aluminum, carbon fiber, or threads of synthetic fibers. The most common spoke is steel, which may be either stainless steel or carbon steel. Both carbon steel and stainless spokes will be magnetic. Carbon steel spokes are strongly attracted to a magnet. However, stainless steel is weakly attracted to a strong magnet. Spokes will come in different lengths to fit various rim and hub dimensions. Spokes are also available in different finishes. Spokes are made in different diameters as well as shapes. This common spoke is 2 millimeters in diameter its entire length. However, a butted spoke will vary in thickness. This one is 2 millimeters at the end, but is 1.7 millimeters in the middle. A bladed or arrow spoke is shaped to give an elliptical or blade-like appearance. The unthreaded end of the spoke traditionally features a J-style bend. The J-band has this head that is held at the hub flange. An alternative to the J-band is the straight pole spoke. There is no bend at the end of the spoke. Rather, it simply ends in a head, much like a nail. Hub flanges must be specially designed for the straight pole spokes. The spokes form a pattern as they connect the hub to the rim. We call this a cross pattern or a lacing pattern. We count the crosses of one spoke as it travels from the flange to the rim. Beginning here at the hub flange, this spoke crosses another spoke here, then here for the second cross, and finally here at the last crossing before reaching the nipple. We call this common lacing pattern a 3-cross. However, this wheel is an example of a 1-cross, crossing only once on this side. But on this side, it does not cross at all and is called radial. For purposes of truing, the cross pattern doesn't matter. The nipple is the nut of the spoke system and is used to change the pulling force or tension in the spoke. These are commonly attached to the rim. However, there are exceptions. These nipples attach at the hub. Although less common, nipples can be made of steel, or can also be made of aluminum to save a little weight and add some color. However, the common bicycle wheel nipple is made of chrome-plated brass. The most common nipple design has 4 wrench flats and is turned by using a spoke wrench. When determining what wrench to use, it is best to use a caliper to determine the width of the flat. Using a spoke wrench that is too large will round the corners of the nipple, so it is important to use the smallest wrench size that fits over the nipple. There are also specially shaped nipples which require special wrenches. Rims can also be manufactured with nipples hidden inside the rim, requiring a special wrench to reach them. Spoke wrench selection is an important part of wheel truing. See our article on spoke wrench selection here. Hubs act as the center of rotation for the wheel. Hubs are commonly made of aluminum and are designed in many different widths. The outer body will have flanges on the left and right side to hold the spokes. Rear hubs are designed with a mechanism for attaching sprockets. Hubs may also be designed for a rotor disc if the bike uses disc brakes. A bearing system in the hub allows the outer shell to rotate around the axle. Hubs attached to the frame or fork. Three common methods are a threaded axle with nuts on either side, a hollow axle designed for a skewer and a cam mechanism that applies pressure to hold the wheel in place, a through axle system where a connection pin is inserted through closed dropouts and the hub and threads into the frame or fork. Wheel truing is the process of using a spoke wrench to change the spoke tension to improve the run out or spinning straightness of a wheel. As the nipple is tightened, it pulls on the spoke. Because the material is somewhat elastic, it pulls on the hub and the rim, creating tension. When all the spokes are properly tight, they create a pattern of opposing forces that suspend the rim around the hub. For example, in this section of rim, these spokes are pulling the rim to the left and are opposed to these spokes pulling the rim to the right. The wheel will become strong and spin straight if all the spokes are correctly tightened. There are four basic aspects to good wheel truing. One is the lateral or side-to-side wheel truing. Two is the radial or up or down truing. Three is the centering or dish. And four is the overall tension. All of these are covered in our wheel playlist. Lateral truing is the side-to-side correction of wobbles or lateral deviations as the wheel spins. When truing wheels, generally begin by first correcting the lateral or side-to-side aspect first. If we watch here at the truing stand indicator, we can see this slight side-to-side motion. This wheel, we would say, has adequate lateral truing. But this rim has quite a bit of lateral air. With a lot of lateral air, the tire can even rub against the frame. Adjusting the tension of specific spokes can move sections of the rim to help correct lateral airs. However, there are limits to what changes in spoke tension can accomplish. If the rim metal has been bent in a crash or by impact, it may not be possible to get it adequately straight. The wheel roundness, or its amount of up and down movement as it spins, is its radial trueness. Radial truing is adjusting spoke tensions to correct issues of roundness. Again, if the metal of the wheel was bent by impact, the results may be limited. The two wheels of the bike should be aligned to one another as well as to the center plane of the bike. We can see this wheel is off center in the frame. The dish, or the centering of the wheel, can be corrected by adjustments to spoke tension. Much like any other fasteners, spokes have a range of acceptable tightness or tension. Wheels with extremely varied spoke tension will not stay true or spin straight for very long. Additionally, wheels with spokes that are too tight or too loose can cause problems. And that is the basic overview of how all the component parts fit together on your wheel, on your bike, and in your wheel truing.
The bicycle wheel is a hoop with a set of spokes that connect it to a hub. The spokes pull on the rim from both the right and left side. Wheel truing is the process of using a spoke wrench to change the spoke's tension in order to improve the spinning straightness of the wheel. It is this tightening and loosening of spokes that we'll use to manipulate spoke tension to true our wheels. Before we get started, let's talk about some common tools you'll need to start truing your wheels. First, we need to hold the wheel steady as it spins. One way to do this is to use a truing stand like these from Park Tool. These are common in bike shops and adjust to many different hub widths and different wheel diameters. Truing stands help isolate truing problems and allow for easier and faster work when truing. If you don't have a truing stand, you can use the bike to hold the wheel. The bike should be in a position so the wheel can spin freely. We need a stationary indicator that will help find lateral deviations. A truing stand has built-in indicator fingers that can be adjusted in and out from the rim to help us easily identify these deviations. If you are truing in the bike, you can make an indicator by attaching something to the frame like a zip tie. These can be moved in and out to show deviations as the wheel spins in the frame. Put one on each side of the rim. Depending on how your bike is set up, you may need to get creative with your indicator placement. You'll also need a way to turn the nipple at the end of the spoke. We increase tension by turning the nipple, or the nut of the spoke system. Looking at the nipple from the outside of the rim, you will turn it clockwise to tighten and counterclockwise to loosen. Working on a truing stand, however, we perceive the nipple as upside down. So this direction is tightening the nipple. When working in the bike, the nipple is right side up, and this is tightening for the nipple. Spoke wrenches come in a variety of different sizes to fit different size spoke nipples, and it is important to use the correctly sized wrench. Too large a wrench will give a sloppy fit that will likely lead to rounding the corners and damaging the spoke nipple. If the bike wheel uses a common square-shaped nipple, best practice is to measure the wrench flats using a caliper. This gets you the wrench size that fits the nipple as snugly as possible. Otherwise, a multi-sided wrench such as the SW7.2 from Park Tool fits the three most common square nipple sizes. There are many different sizes and even shapes for spoke nipples, which we cover in this article on spoke wrench selection at parktool.com. If your wheel has bladed or flat spokes like these, they can twist around as the nipple turns. You need something to hold the spoke to prevent this, like the BSH4. When you begin truing, if the nipples seem hard to turn or are creaky, they need lubricant. Put a drop of lubricant where the spoke exits the nipple and where the nipple exits the rim. And finally, if you are just beginning to learn wheel truing, it can be helpful to take the tire off of the rim. With the tire removed, the lateral deviations you're looking for at the rim will be easier to see. Install the wheel in a truing stand. Adjust your indicators so they are near the outer edge of the rim, but not touching the rim. This can help isolate deviations when the rim has a parabolic shape or has stickers applied to it. Spin the wheel and slowly move the indicators towards the rim, watching for where the rim gets close to the indicator. Keep moving the indicator closer until you see it lightly contact the spinning rim. The goal is to adjust the indicator so it just lightly rubs the rim. Bring your indicator in close and then back it out in order to find that light rub. This area of contact is the most severe lateral deviation in the rim. Slow the rim and stop it where the rim and indicator are touching. It doesn't matter if the left or the right indicator is touching the deviation. In fact, we're going to correct deviations from both the right and the left side of the rim to maintain proper wheel centering. Now, determine where to make spoke tension corrections. If the indicator seems to touch over a long area, find the center of that area. This spoke is at the center of our deviation. We need to tighten this spoke nipple coming from the right side of the hub to draw this part of the rim to the right. It is preferable to tighten spokes rather than loosening them. Spokes may loosen themselves over time if they are run too loose, but they will not tighten up on their own. A way to simulate what tightening a set of spokes will do is to give them a squeeze. By squeezing these two right side spokes by our deviation, we can watch how the rim moves when the tension of these spokes is increased. Let's tighten this spoke by turning the nipple. How much you need to turn it will vary. If it is a relatively bad lateral deviation, you will need to turn maybe 1/2 of a turn. If it seems like a minor deviation, start with a smaller turn, maybe 1/8 of a turn. The concept is to make a correction and watch for feedback of what you've done. For this, let's see if 1/4 turn does anything. Move the wheel back and forth through this area to see if there is any progress. It seems better, but it is not completely gone. We need to repeat the process. Move the indicator closer, find contact, and correct. Spin it again, find the lateral deviation, and correct. That was 3 corrections on this side. Let's switch to the other indicator. For stands like the TS2.2, you can use a small hex key under one arm to pull it out of the way. Spin the wheel and move the indicator inward. Find the lateral deviation where it lightly touches the indicator. As you can see here, where we squeeze these spokes on the left-hand side of the wheel, the rim moves to the left. So we will tighten this spoke nipple. Spin the wheel. Now you can see that section of rim is no longer hitting the indicator. Again, adjust the indicator towards the rim to find the next deviation to correct. Because this deviation is longer, we'll tighten these 2 spoke nipples and see if the deviation is gone. We move the rim back and forth through the deviation and we see it's been reduced. Spin the wheel again and move the indicator closer to the rim. Correct the deviation. Now, time to switch back to the other indicator. The wheel's straightness gets better as the lateral deviations are reduced. As the wheel gets more and more laterally true, you can cut down to smaller corrections. So, that's the truing process. Locate, isolate, and correct the deviation. We've seen that as you work, the wheel will become more and more true. But how true is true enough? Well, this is a little bit subjective, and it depends on how the wheel has been ridden. Also how it's been cared for, and what you personally want for your wheel. As a general guideline, you want about 0.5 millimeter or less of lateral deviation. 0.5 millimeter is about 5 sheets of typical printing paper. And this will help you visualize what 0.5 millimeters looks like. Spin the wheel and adjust the indicator so it just barely rubs the rim. At the rub, the distance between the rim and indicator is 0. Sight the lateral deviation to get a sense of their size. This rim has over a 1 millimeter lateral deviation and would be considered to be out of tolerance. It needs a little bit more work. This rim has just 1/2 millimeter of deviation and is certainly acceptable for most uses. However, if it gives you satisfaction to continue and make the wheel spin straighter and straighter, then keep finding deviations and making corrections. This wheel has a deviation of 0.2 millimeters. Sure, you could do more to it, but it doesn't necessarily make the wheel better for riding. After having adjusted quite a few spoke nipples, it's fairly common that the wheel needs to be de-stressed. De-stressing a wheel allows the spokes that were wound up from turning the nipple to unwind. There are a few different ways to do this, but the safest way is to simply ride the wheel. So put it on your bike, take it out for a ride. Expect some pinging and popping noise from the first few pedal strokes. That's common and of no concern. So that's the basic process for laterally truing a wheel. For more
Radial truing. That's the up and down or egg-shaped aspect of a spinning wheel. The wheel of the bicycle is a hoop with a set of spokes that connect it to a hub. Spokes are pulling on the rim from both the right and left side. Wheel truing is the process of using a spoke wrench to change the spoke tension to improve the runout or spinning straightness and roundness of the wheel. It is this tightening and loosening of spokes that we will use to manipulate spoke tension and true our wheels. Let's take a look at some common tools and get set up to begin truing. First, we need to hold the wheel steady as it spins. One way to do this is to use a truing stand like these from Park Tool. These are common in bike shops and adjust to many different hub widths and different wheel diameters. Truing stands help isolate wheel truing problems and allow for easier and faster work when truing. If you don't have a truing stand, you can use the bike to hold the wheel. The wheel should be able to spin freely, such as by putting it in a repair stand. We need a stationary indicator that will help find radial deviations. The truing stand has these indicator fingers that can be moved up and down as well as in and out from the rim to help us easily find these deviations. If you are truing in the bike, you can make an indicator by attaching something to the frame like a zip tie. These can be moved up and down to help show radial deviations as the wheel spins in the frame. You'll also need a way to turn the nipple at the end of the spoke. We increase tension by turning the nipple or the nut of the spoke system. Looking at the nipple from the outside of the rim, you will turn it clockwise to tighten and counterclockwise to loosen. When working on a truing stand, however, we perceive the nipple is upside down, so this direction is tightening the nipple. When working in the bike, the nipple is right side up, and this is tightening the nipple. You will need something to hold the spoke to prevent this, like the BSH4 from Park Tool. When you begin truing, if the nipple seems hard to turn or they are creaky, they need to be lubricated. Put a drop of lubricant where the spoke exits the nipple and where the nipple exits the rim. Finally, if you're just beginning to learn wheel truing, it can be useful to take the tire off the rim. With the tire removed, the radial deviations you're looking for at the rim will be easier to see. Radial truing can be tricky, especially if you're just learning. Expect to go back and forth between radial corrections and the side-to-side or lateral corrections as you work your way around the wheel. Let's define the two basic radial deviations we're looking to correct. As the wheel spins, there is a radial deviation where a section of the rim seems to move inward or toward the hub. We call this a low spot. These can be short, say across 2 spokes. Or these can extend longer, spanning 6 or more spokes. The other type of radial deviation is a high spot, where the section of rim moves away from the hub. Like the low spots, these high spots can span a short or long section of the wheel. The wheel, of course, can have a mix of both high and low spots. Because the rim is somewhat flexible, we tend to average out both until we get an acceptably round wheel. Install the wheel in a truing stand or back into the bike. Before beginning on radial deviations, check that the wheel is reasonably laterally true. If you are not familiar with this procedure, see this video, Lateral Wheel Truing, here. Does not matter whether you are paying attention to the left or right edge of the rim sidewall. In fact, to keep things simple, pull one arm away and block it with a small hex wrench. Spin the wheel and adjust your indicator so that it is sitting below the outer edge of the rim, but not close enough to touch. If you're using a Park Tool truing stand, use the top of the indicator tip as your reference. Begin by locating the high spot by slowly moving the caliper arm upward until you see or hear it lightly contact the spinning rim. Isolate this high spot by slowly moving the rim back and forth through this area to see where it begins and ends. Correct this radial deviation by moving this section of the rim toward the hub. To make this correction, we're going to tighten spokes from both sides. That's because spokes not only pull from the right and the left side, they also pull the rim toward the hub. We can simulate what tightening will do by grabbing a spoke from the right and left side and squeezing and seeing that that section of rim is going to move toward the hub. For now, give each of the high spot areas 1/2 of a complete turn. The rim is no longer rubbing, so the high spot was reduced. Now we repeat the process. Spin the wheel and continue to locate, isolate, and correct. You may also find longer high spots. This one seems to involve 5 spokes. To keep this simple, round down to 4 and tighten only 4. If the 5th spoke was needed to correct the high spot, it will show up again as you continue to locate, isolate, and correct. As you proceed, it can occur that there will be some lateral errors created as you correct the radial problems. Check that lateral true is acceptable about every 3 or 4 radial corrections. Typically, it is best to begin your radial truing with the high spots. After correcting these, the low spots won't look so low. Again, move the indicator below the rim, but not touching it. Spin the rim to locate the gaps between the rim and the indicator. Find that area where the gap looks the largest. Remember earlier what occurs when two spokes were squeezed. Watch the rim and note that as the spoke tension was relaxed, this section tends to move outward, away from the hub. Isolate the center of the slow spot by moving the rim back and forth in this zone. The section of rim is pulled too close to the hub and needs to be moved away. In this zone, we have two spokes. Loosen each 1/4 turn. Move the rim back and forth through the low area to see if there is less of a radial problem. It may take a few attempts to see progress. Continue the process to locate, isolate, and correct. Again, check for lateral errors every few radial corrections. We have seen as you locate, isolate, and correct, the wheel's becoming rounder and rounder. But how round is round enough? Generally, for radial deviation, a 1 millimeter tolerance is going to be good. Remember, a tire's going to go on top of this, and they're not exactly perfect. So 1 millimeter, that's about 10 sheets of printed paper stacked together. That is what our gauge is going to look like. We're going to spin the wheel and slowly bring up the indicators until we get a light rub. The light rub indicates we have 0 distance between the indicator and the rim. From this point, slowly spin the wheel and sight the gap looking for the largest point. Is the largest gap greater or less than 1 millimeter? This appears here to be the largest looking gap. Using our gauge, easily goes in. This wheel appears to be out of tolerance. It needs more work before we're round enough. If it gives you satisfaction to continue to make the rim rounder and rounder, continue with locating, isolating, and correcting even smaller and smaller deviations. But realize, at the same time, there's going to be some rims where repair is not possible with the spoke wrench. The rim has been impacted and is deformed. The spoke wrench is going to be unable to return it to a normal shape. One aspect to finish your truing is called de-stressing. After you work on the wheel and you've turned a lot of the nipples, the spokes tend to wind up. They need to be brought back to a neutral position. The safest way to do that is actually just go ride the bike. As you ride, the wheels tend to detension slightly. It may pop and ping a few times, but then spokes are stabilized and you're done. Go for a little ride. And that's the basic process for radially truing a wheel. Bicycles are designed for the front and rear wheel to be centered to the mid-plane of the bike. If the wheels are not centered or out of dish, the bicycle can handle poorly. The wheel and rim of the bicycle should be centered to the middle of the frame or fork, which also places the rim over the middle of the hub. For bikes using open dropouts, the rim is centered between the hub lock nut faces, which are the contact points for the frame or fork. For through-axle wheels, the face of these hubcaps are the contact points for centering the rim. On front wheels without a rotor disc, such as bikes with rim brakes, both the left and right hub flanges are set equal distance to the middle of the hub. The rim will be centered to the hub contact points as well as being centered between the left and right hub flanges. On this rear hub with sprockets, the rim is also centered to the middle of the hub, halfway between the frame contact points. However, the left and right flanges are not equally distanced from the hub center. The drive side hub flange is offset toward the inside to allow room for the sprockets. Although the rim is centered to the two contact points, it will not be centered to the middle of the two flanges. Here are some recommended tools when working on centering. A dishing tool such as the Park Tool WAG4 or WAG5. A spoke wrench that is compatible with your spoke nipples. Properly sized spoke wrenches are very important, See this article at parktool.com for more information. Tire levers if you need to remove the tire, and a wheel chewing stand can be very helpful, such as the Park Tool TS 2.2 or TS 4.2. The most accurate method of checking wheel centering is with a dishing tool. If you don't have one, here's a visual test that will give you an idea of the centering. Sight how the wheel is sitting in the frame or fork. Does it appear off to one side? This front wheel appears to be well centered to the fork. However, this bike's rear wheel doesn't appear to be well centered. It looks like it is off toward the left side. If it looks off center, double check that the wheel was mounted correctly in the frame or fork. To be corrected, this rim needs to move to the right, a process described later in this video. Using a dishing tool, such as the WAG4 or WAG5 from Park Tool, is the most accurate method for checking wheels for centering. Before using a dishing tool, begin by checking the lateral truing straightness of the wheel. If the wheel is badly out of true, the dishing tool will not be as accurate. Correct lateral truing errors before using a dishing tool. For lateral error correction, see the wheel truing playlist here. To use the dishing tool, it is easiest to remove the wheel from the bike. For consistent work habits, lay the wheel flat on a bench with the right side or drive side facing up. If you are using the WAG5 or similar tool, be sure the legs of the tool contact the rim and not the tire. If necessary, deflate the tire and fold it back so the tool legs are on the rim. For through axle wheels, the WH1 makes a nice wheel holder. The WAG4 has sliding feet, allowing rim contact even with the tire still in place and inflated. With the feet of the tool on the rim, lower the sliding indicator until the end rests on part of the hub that contacts the inside face of the fork or frame dropout. On through axle wheels, that is the face of the end cap. These 3 points of contact represent the centering of the rim relative to the right side of the hub. Snug the slider knob and lift the tool. Flip the wheel over and compare this right side template to the same points on the left side. There are 3 possible scenarios you might encounter. The first scenario is you see no significant gap at the hub. Both left and right rim measurements match relative to the hub. This means the rim is well centered to the hub and the wheel needs no centering correction. Now let's look at a second scenario. This wheel uses a quick release skewer and is from an open dropout fork. The skewer can stay in place when using the Park Tool dishing tools. Starting on the right, set both feet so they contact the rim. Next, lower the indicator to the hub lock nut face. Flip the wheel to the left side and compare the reference set from the right side. With this wheel, we have a fairly large gap seen at the hub. This wheel is clearly not as nicely centered as the through axle wheel in scenario 1. However, a wheel need not be perfectly centered to be fully usable. The center of this wheel will be offset to the mid-plane of the bike by only half of the gap seen here. Generally, if the air gap seen at the hub is about 1 millimeter or less, the wheel is only off-center by less than 0.5 millimeter when in the bike, and that should be considered adequately centered for any use. The scrap piece of gear cable is 1.2 millimeters, which is pretty close to 1 millimeter. It makes a simple and available go, no-go gauge. If the cable fits in the gap easily, like here, the wheel needs correction. Here is another measuring test if the wheel uses threaded axles. A threaded axle is commonly a 1 millimeter pitch. We can see about 3 threads here between the indicator and the lock nut face, so we have about a 3 millimeter error. This rear wheel will demonstrate the third possible scenario. After setting the tool on the right side of the wheel, flip the wheel to compare the 3 contact points to the other side. Here, when the tool is arranged so both feet are placed on the rim, the indicator sits below the lock nut face. Again, if the difference between the indicator and face is within 1 millimeter, it should be considered within tolerance. This example looks like it might be close to 1 millimeter. To get a gap you can measure more easily, reset the dishing tool using this left side as the beginning reference side. With this double flip of the wheel back to the right side, you will find a gap between the indicator and the axle end face. Our scrap piece of cable indicates this wheel needs correction. If a wheel needs a centering correction, it's important to understand how the rim moves relative to the hub. When there is a gap between the hub lock nut face and the tool indicator, the rim needs to move toward the side opposite the tool. This rim needs to move to the right, the non-rotor side, which will effectively move the hub left. That will reduce the gap between the indicator and the hub. This is an easy place to get confused and move the rim the wrong way. But here's a test to help visualize what's going to happen when you tighten one side. Let's simulate what tightening spokes on one side would do. Squeezing a pair of right side spokes near the dishing tool foot moves the rim, much like tightening all right side spokes. We can see the gap getting smaller. That tells us tightening the right is the way this rim needs to go. To move the rim relative to the hub, we use changes in spoke tension from one flange. The spokes in the rim are coming from the left and right flanges. Each side is pulling the rim toward their own flange. Tightening only spokes from the right flange moves the rim to the right. Tightening only the left side spokes moves the rim toward the left. However, because the rim has tension from both left and right side spokes, we can also loosen to make corrections to centering. Loosening only the left side spokes also moves the rim to the right because the right side tension will pull it over. Loosening only right side spokes will move the rim to the left. Keep in mind that tightening one side raises the overall wheel tension, even of the side you're not tightening. For example, tightening the right side moves the rim to the right, but it also raises the overall spoke tension, even of the left side spokes. This is when it's a good idea to get a sense of where the wheel's at for tension. With enough experience, you can squeeze and get a sense of this, but this is why we'd recommend a tensiometer like the TM1. Here, check a few spokes. This wheel we're looking at, it's pretty low tension. Tightening the right side of this wheel to fix the dish would be a good choice. It will fix the centering error and raise the overall tension. On wheels where the flanges of the hub are different to the center of the hub, such as rear wheel with sprockets, or on front wheels with the rotor disc, you're going to see differences of left and right side spoke tension. The side that is inset or further in is going to have higher tension. You could measure it and even feel it on these wheels. This side, for example, feels tight, but squeezing the non-drive side feels looser. That's simply the engineering of these wheels and is a normal thing. And this is why we pay attention to the tightness of the inset side, the tighter side. The other side will simply be lower when the dish or the centering is properly set. When available, install the wheel into a truing stand with the right side on your right as you face the stand. This helps you orient yourself to the wheel so you can remember which way the rim needs to move. Adjust the caliper indicators out of the way. The dishing tool has already provided the most accurate information on which way to move the rim. This particular wheel has an error seen at the left side of the hub. The rim needs to move to the right. Use the tire valve hole as an easy, recognizable starting and stopping point. Select a spoke from the right flange that is adjacent to the valve. When just learning to make dish corrections, it is best to work in small increments. Install the spoke wrench fully on the nipple and take note of the wrench orientation. Turn the wrench 1/4, which is turning the wrench 90 degrees. Seen from looking over the nipple, this is the way you will tighten. After turning this first right side spoke nipple 1/4 turn, advance to the next same side spoke and again tighten 1/4. Continue this way all the way around the rim, tightening only right side spokes until you were back to the starting point at the valve hole. It is common for the wheel to develop some minor lateral truing issues from this change in tension. Spin the wheel and correct any lateral error. Because the rim is moved relative to the hub, you need to reset the dishing tool starting again from the right side. We want to see an improvement and a reduction in the air gap. If the error is still too large, it may take several attempts to get the rim centered. This gap is smaller, so it's getting better. Repeat the correction, again using 1/4 turn. Check the dish reference from both sides and repeat as necessary until the wheel shows 1 mm or less gap at the hub. In this rear wheel, we found that the rim needs to move toward the non-drive side. On a rear wheel, a concern for maximum tension is the flatter side, the drive side that's inset more. A check of this side shows this wheel is actually very tight tension. Although we could fix the centering by tightening the left, it's going to rocket the tension beyond where we want. So in this case, we would loosen the right side, help back down the tension, and correct the dish. Loosen the right, check the lateral, check the dish until it's in tolerance. Begin at the valve hole and loosen each drive side spoke 1/4 turn. Check the lateral true and check the dish. On a wheel like this one that has good overall tension but bad dish air, it makes sense to make corrections to both sides. However, don't do your tightening and loosening in one pass. First, loosen the side that needs loosening, correct lateral air. Next, tighten the side that needs tightening. Again, check lateral air. Finish by checking the dish and see if it gets within tolerance. And that's how we check wheel centering and how we correct wheel centering to get the rims in the middle of the bike, the frame and the fork for the best handling possible.
In this video, we'll be going over spoke tension, why it's important, how to measure it, and also how to adjust. Spoke tension is the amount of pulling force being exerted along a spoke. It is typically measured and called out by component companies in kilograms of force or in newtons. When truing or dishing a wheel, the mechanic is making adjustments that affect spoke tension. Good wheel tension is not just about an individual spoke though. It's about the consistency of all the spokes coming together and creating a nice rigid structure. So why is spoke tension important? Well, without it, things would tend to fall apart. When you're out for a ride, your wheel flattens slightly where it meets the ground. As this happens, the spokes at the bottom of the wheel lose some tension. This cycle of gaining and losing tension happens throughout the entirety of your ride. If a wheel's tension is too low, it can cause the spokes to relax too much during a ride, creating a snapping effect and causing excess stress to both the spokes and the rim. This can lead to detensioning, which is when spokes lose tension over a short amount of time. This leads to breaking spokes, rim fatigue, and a not so durable wheel that will go out of true more often. At the other extreme, too high of spoke tension can cause cracks in the rims, broken spokes, or even damaged hubs. Before we get to measuring tension, we should really figure out what our tension should be. Consulting with your rim manufacturer's website is a great place to start. Most rims have suggested ranges from about 100 to 120 kgf. This is assuming there is no pressure in the tire. As for measuring spoke tension, one method is to squeeze the spokes. Though not foolproof, squeezing spokes from a wheel you know to have good tension is a way to get a sense of what acceptable tension is. Squeezing is a more accurate way of measuring spoke tension than, say, perceived effort when turning a spoke nipple. Like any fastener, the nipple will tend to become more difficult to turn as tension increases. But this doesn't always mean that the tension is too high. It could have corrosion or just be at the end of the threads. The best way to measure spoke tension is with a spoke tension meter, like the Park Tool TM1. Spoke tension meters flex a spoke between two posts with a calibrated spring. This deflection is shown on the meter's scale. To accurately use the Park Tool TM1, you're going to need to know the diameter of the spoke and also the material of the spoke. This spoke is a round steel spoke. The diameter in the middle of the spoke is 1.8 millimeters. When using the TM1, make sure to place the two fixed posts on the narrowest parts of the spoke, or in the middle of the spoke. This steel spoke is giving us a reading of 15. Looking at the TM1 chart, we find the steel round spoke section and scroll over to our spoke's diameter, 1.8 millimeters. With our TM1 reading of 15, that places the tension of our steel round spoke right at 58 kgf. This rim's manufacturer calls out a max tension of 110 kgf. We are going to set a tension goal for this wheel of 100 kgf on average, which for our spokes is a reading between 20 and 21 on the TM1. Continue on by checking one entire side of the wheel before making any tension adjustments. Write down your results or input them into the wheel tension app at parktool.com/WTA. When we check the left side of this rear wheel, we notice that these readings are lower than the right side. This is due to the fact that the spokes come out of the hub at different angles. The angle that a spoke leaves the hub is often referred to as the bracing angle. When the spoke has more angle, that means that it has more mechanical advantage and will need less tension to counter the opposing side if the opposing side has less of a bracing angle. This is seen on rear wheels and front wheels with a rotor. Your tension goal applies to the side with more tension. The opposing side will simply have lower tension when your dish or centering is correct. Armed with the knowledge of our wheel's current tension, we can start to make changes. When adjusting spoke tension, it can really help to have something to hold your wheel while you work. The Park Tool Truing Stand is a fantastic option. You'll also need a properly sized spoke wrench to turn the nipple at the end of the spoke. There are many different sizes and even shapes for spoke nipples, which we cover in this article on spoke wrench selection at parktool.com. When adjusting a wheel's tension, our number one goal is consistent spoke tension, or what we call good relative tension. On this wheel, we measured and they were a little bit inconsistent from spoke to spoke, but overall they were a little on the low side. To correct this wheel, we want to raise its overall tension. Since this is a rear wheel with different bracing angles on each side of the hub, increasing tension may change the dish slightly. With that in mind, let's give the spokes on the drive side 1/4 turn each, and those on the non-drive side 1/8 of a turn to start. Now that we have gone around the entire wheel, let's check what our work has done. We'll measure with the TM1 and plug our data into the WTA at parktool.com. We've increased the right side tension on average by 25 kgf, but we have a bit further to go, so let's repeat the 1/4 turn on the right and 1/8 turn on the left. After these adjustments, we can see our tensions have gotten closer to one another, and our relative tension is very close to our target of 100 kgf. If when measuring your wheel's relative tension, you find that the tensions are too high, you're going to need to bring those tensions back down. The process of reducing tension is very similar to increasing tension. You'll just be turning the spoke nipple the opposite direction. The tension of this wheel is too high by about 30 kgf. Because this is a front wheel with equal bracing angles on the left and the right side, loosen each spoke by 1/4 turn. When spoke tensions are this tight, 1/4 of a turn will lower spoke tension quite a lot. Go around the entire wheel like this, and then recheck your tensions. Using our TM1, we can see that our tensions are already down to 120 kgf. You may notice when taking readings that there's some fluctuations in the spoke tension on one side. If the tension fluctuates widely, your wheel may benefit from tension balancing. Tension balancing is when you increase one spoke's tension or decrease another spoke's tension to get the relative tension to be the same. A well-balanced wheel is going to stay true for longer and increase the life of your spokes. A wheel with spokes that are within plus or minus 20% of the wheel's average spoke tension is generally considered to have acceptable relative tension. You will have outliers, however. When addressing these spokes, think about how tightening or loosening them will affect the trueness and dish of the wheel. Here, I will loosen this spoke and tighten this other to keep the relative tension the same. We call this the zone of influence. The zone of influence, tension balancing, and more is covered in detail in our WTA video. So how do we know when our wheel is properly tensioned? Well, if your wheel has good lateral true, good radial true, is properly dished or centered, and your tension on the high tension side of your wheel is up to manufacturer spec, that's a good place to start thinking about stopping. You can keep on fine-tuning your wheel to finer and finer tolerances, but you don't have to have a perfect wheel to enjoy the ride. So that's the basic process for how to check and adjust your wheel's spoke tension.